Hi. In this video, we're going to conclude our series on nonlinear programming. Thus far, we've established what are Kuhn-Tucker conditions for finding maximum. In the case where we have constraints in the form of inequalities. However, those conditions are necessary. However, again, there are circumstances under which those conditions become sufficient. And what you see over here in front of you is the Kuhn-Tucker Sufficiency Theorem. And it says that we can be sure that what we found using Kuhn-Tucker's conditions is going to be a maximum when three requirements are met. First, the objective function f of x is differentiable and concave in the non-negative ortant. Each constraint function gi of x is differentiable and convex in the non-negative ortant. And finally, the point x with asterisk, so our optimum that we found, satisfies the Kuhn-Tucker maximum condition. Okay, and look, this one is not very bad. We can easily check if our function is concave and our constraints are convex. We know how to do it. All we need to do is to calculate derivatives. And if those conditions are met, we can be 100% sure that what we found is actually a maximum. However, we should also keep in mind that those conditions can be somewhat relaxed. And this is what we get from the Arrow-Enthoven Sufficiency Theorem. Look, here basically we are changing requirement of function f of x of being concave to being quasi-concave, and our constraint from being convex to being quasi-convex. Additionally, we get point D where we have four alternatives, and only one of them needs to be true for the maximum that we found, for the point that we found to be a maximum of the function. Now, on the exam, we're not going to be using it. However, I really want you to know that if you're going to be dealing with a problem like that, we should use either Kuhn-Tucker Sufficiency Theorem or Arrow-Enthoven Sufficiency Theorem to be sure that we actually find a maximum. Okay, and finally, there is one more thing we should discuss that we have not discussed previously. And this is a constraint-qualification test. Look, as it turns out, there are circumstances under which we've got a very problematic constraints that can lead us to a wrong answer. However, again, we've got a very simple test that can give us the answer whether this is a situation in which we are on or isn't. And look, again, what we want to know now is that every constraint function gi of x is differentiable and quasi-convex. There is a point x0 in the non-negative ortant such that all the constraints are satisfied, strict inequalities at x0. And again, one of the following is true. Every gi of x function is convex, or the partial derivatives of every gix are not all zero when evaluated at every point x in the feasible region. However, it is really important to notice one simplification. Look, if we have linear constraints, then the constraint qualification test is always fulfilled, and we don't even need to worry about it. And those are actually the constraints we were considering this time, and in various economic applications they are enough for us to use. Okay, and before you start to worry, I want to say that this part is not going to be on the exam. However, I would like for you to know this. All those three theorems that we've just discussed are going to be available along with other notes I have provided for you. And at this moment, I can just thank you for participating in this course and wishing you the best of luck in the future. Take care and hopefully see you again in dynamic economic analysis. Take care.